Hello everyone, welcome to TuxRiders. Back to theoretical discussion. From this video we want to start to talk about the theory of finite element, a bit of the math behind, but still not too much into the details. We want to talk about all the things that you need to know about finite element to take advantage of it in your modeling projects. Let's go for it. So in the previous videos of this series, Applied Numerical Computing series, we discussed about the basics of Python ecosystem that was needed for this course, including NumPy, SciPy, and other fundamental libraries. And we discussed finite difference method in detail, or I mean in the details, in the level that we needed it. So that was a coverage of the basics of finite difference, approximation of the solution of partial differential equations. And if I want to show you, it was here. You can find a link in the description or in the TuxRiders website. There are two ways. To access the content. One is via the GitHub link, and the other one is via the published video series, an easy introduction to applied numerical computing, and then the materials in this GitHub repository. And if I want to just show you quickly the videos, these were the videos for the essential of Python. Essential Python concepts, and then finite difference for ORDs and PDs, and then the numerical schemes for different types of PDs actually. But this is the repository via GitHub. If you go directly to GitHub, the homepage of TuxRiders and GitHub, you can click in the introduction to numerical computing, and this is actually the same repo as here. So these are the content and the Jupyter notebooks for the scientific programming with Python. And then for the finite difference method, these are the topics that we discussed, including also some talks on explicit and implicit schemes, and then the stability conditions and this kind of stuff. But from this video, as I said, we want to start on finite element method. And we previously discussed finite element, not in detail, but we had a brief introduction to that in the introduction to finite element modeling series. You can find the link in the description or via the cards on the top of the screen. And in that series, we used different tools, finite element tools, to solve a single problem. And in one or two videos where we use FreeFEM and Phoenix, I said that we need the weak formulation of the partial differential equation, and for deriving that we need to know finite element. We need to know the theory of finite element, and this is actually very essential when you want to work with those tools, which there are pros and cons for any tool, but for those tools, the main advantage is you have a full control and solution, and you have a high level of freedom to modify different aspects of the numerical of the solution and generally the simulation. So you can have really high quality works using that. And in TuxRiders, our main focus is on FreeFEM and Phoenix, and that's why we need to know finite element theory a little bit. So that's why I said that the title of the video is all you need to know about finite element. And I try to say it, short, in less than 1 hour, in 2 or 3 videos. And then that's actually all the essential things that we need to know to get started. And then this topic is based on a book. I have the references here. So I've said that this is by me, but this is actually, the repository. But the book is from a great book that is called, Introduction to Numerical Methods for Variational Problems. And this is a great book, maybe the best I've read so far for variational formulation of finite element method, written by Professor Langtongen and Professor Mardell. great guys, although Professor Tangen unfortunately passed away a couple of years ago. But I met Professor Marl 2 weeks ago in a conference in the University of Oslo. These great guys, and they have published a lot of things about finite difference and finite element, and this book is about finite element. And so you can find the source code of the book in the links here, and there is also a hard copy version of that published by Springer, I think, and you can find the links, all the links here. So these are actually the topics that you can also find here in the finite element method. And, I have added some free-form codes to that as well. But this is actually not something that we want to discuss in this series, in these videos. I want to just talk about the theories. And then later on in a dedicated series, we will discuss the free-form and Phoenix codes from scratch, from the basics to more advanced topics. So for the finite element, let's start with the first Jupyter notebook, then they can go one by one. I will discuss about the function. Oh, maybe I need to. I will discuss the function approximation in this video, and in the next video I will discuss about variational formulation, and in the last video we will discuss the time-dependent problems, and also dealing with nonlinearity, two important aspects that we need in TuxRiders. And these are the things that we want to cover from this book. So actually these 3-4 videos will be a summary of this great book. So all the things that you need to know about the finite element extracted from this book. If you want to know more about it, you can go through this book, through these Jupyter notebooks thoroughly, and then read it carefully, and then there are a lot of things that you can learn from this. So let's start with the first notebook. I click on this quick overview of finite element method, although this is something that I said we already discussed about. So finite element is very similar to finite difference. It's a method for approximating the solution of partial differential equations. I hope that the font size is enough, so I think this is a little bit better. So when we want to solve an equation like this is the finite difference approximation. And for finite element, as we discussed before, we need to define a finite element space from which we define some functions, a trial function, test function, and then we derive the weak formulation of an equation, of partial differential equation. In this case, this is a Poisson equation. And then we perform the integration by part. These are the things that we want to discuss in these theories. And then we can use actually a tool like Phoenix. In this case, you can see the implementation in Phoenix for that. And then in Phoenix, we define trial function, test function. And it's very easy to define the bilinear part and the linear part of the equation. These terms will be discussed in this series. And then the Phoenix interface provides us with a very simple, let's say, function that we can call to say that, solve this equation for us to get u. And then we can easily also plot it or save it to a VDK file to be post-processed by ParaView. So the code will be as simple as this, but there are some theories behind this, especially when you want to work with more complex PDEs. You need to know the theories, or some of the theories, let's say. So we start with a function approximation by global functions that is followed later by finite elements. So function approximation by finite element, we start with this one. If we can understand the concepts of function approximation, we already know the concepts of finite element, because finite element is, as I said, is a tool, as a method to approximate the solution of differential equations. And for doing that, we use a kind of approximation that, as you can see here, by a sum. So approximating the unknown function by a sum. So we say that, for example, in this case, we have a function that we want to approximate, and then we say that it's actually a sum of some unknowns multiplied by some of the functions that we know. And this is very important. This, for example, here is called psi, but this psi function is very important for us, and this is what this notebook is actually all about. So let's scroll down and then see what we want to do for this. So this is a great example provided by this book, in the book that I said, that starts the concept of approximation with vectors. If we can get this, then the rest of the story is very simple. So we want to approximate a vector, in this case this black vector. We want to approximate it using the vector that is depicted in green. So in this case, that is a kind of projection. So projection of this vector on this one. But if you try to remember the concepts of like geometry or algebraic geometry, you can see that in this case, what you needed was actually kind of unit vectors. In this case, you can see that we have a unit vector here. And then you can say that for approximating this vector, the black one, and this green one, we define a unit vector. And then we say that this is actually c times multiplied by the unit vector. So that was actually what was written above, and in higher dimensions you can have more unit vectors. So if you assume that a function is a vector, or let's say this is an analogy, then this kind of function approximation in finite element is finding actually. It is to investigate and finding the coefficients that can be multiplied by some unit vectors or unit functions that they can approximate the main function. And this analogy, with analogy to vector space and vector calculus, vector geometry, you can easily understand this. So this is a great example to start with, to say that when we want to approximate a vector, we define a space. In this case, we have like only one vector here, unit vector, and then we say that actually that's the C0 times the unit vector. And there are different things that we can apply here. Then we want to measure the error, and this is actually where the story starts. To measure the error, you can say that it is actually, this is the main, f is actually the main vector, and this is the approximation. And this is least square method, that you need to actually, the root square of the multiplication of the vector, in this case the error. And for doing that, when we want to have this is a very theoretical actual explanation of the thing that you will see more in the book. But if you want to have the minimum or the best approximation, is actually the best approximation is the one that minimizes the error. And it means that if we want to minimize the error, we should have the partial derivative of it regarding the coefficients equals to 0. So this is where the story begins, and then it starts to prove, this is actually a mathematical proof, that the error is 0 when we have those basis functions. It can be used interchangeably as the error. But this is very theoretical, as I said. There is another thing that is actually the projection method. This is a mathematical proof, but you can see that the minimization, or finding the minimum, occurs when the error is perpendicular to the approximation. That's what I said, because this is the inner product. As you can see, this is the inner product of the error and the approximation, and we see that it is 0, meaning that they are perpendicular. So this is actually the method of projection, and later on we will see that this is actually the start of finite element. This is where finite element starts. And when we have more vectors, let's say more space, like higher dimensions, in this case you can see that it is n-dimensional problem, like in 2D and 3D. For example, in this case for 2D, you can say that I have x and z, and then you need to define the vectors, the unit vectors like this. So and you know that these are I and j usually. So these are the unit vectors. And then for higher dimensions, 2D, 3D, 4D, it can be the same. So this is actually for approximating vectors. So you can see that how simple is that. So for higher dimensions, it's the same principle. We want to minimize the error. And while doing that, we reach a point that, you know, it started to say that, yeah, the partial derivative should be 0 respecting all the components. And as we go on, you can see that we reach a point that we see these very, very familiar equation that is actually nothing but ax equals b. So the method of projection, and we want to actually derive the error of approximated vectors, it always yields to this equation. That is actually, as you can see here, the inner product of the vector of the unit vectors and also the inner product of the vectors and the main function that we want to approximate, the main vector that we want to approximate actually. This is very interesting. This is very interesting that by following this, we yield to this point actually. So now the story is going to be even more fun. And that's where the Galerkin term, the Galerkin method comes into play. And you may have heard about Galerkin. Galerkin is actually a term that you hear a lot when you want to work with finite element. And that's actually the basic methodology in finite element formulation. And here you can see that it is nothing but actually the projection method. So it says that if you want to have the minimum, you can see it's minimizing the error is equivalent to demonstrating that E is orthogonal to all the unit vectors that you wanted to use. So, or let's say all the approximated quantities like C, the coefficient multiplied by the unit vector. And that's actually the Galerkin method. So you can see here that it says that the inner product of E and V equals 0, and then we substitute the V with the approximation, and then we go on. And then if you substitute and start to derive all the mathematical equations, we see an equation like this, which is something that you will see a lot in the future. That is actually, this is what we call the linear term, and this is where we call it with bilinear term, and that's why it contains these unknown coefficient. So we know all these things because these are the unit vectors that we choose, and these are the inner products of the unit vectors depending on the dimension of the problem, and we are looking for the C. If you have a closer look at this, you see that it is actually ax equals b. So, welcome to the finite element theory. This is where it starts. Let's go on and then see, for example, the approximation principles for functions. So for functions, if we assume that we have like in the functions, we have the same principle, we have the same the function space. But in functions, we do not have inner product. And instead of inner product, we can perform the integration. So it's in this paragraph, it says that if the inner product of two functions is actually similar to the piecewise summation of each component, meaning that it's an integration of the multiplication. So it is as simple as that. And then minimizing the error, we can have exactly the same thing with similar to what we had for the vectors A and B, but in this case these are the functions. So we are already there, We approximate a function by choosing some basic unit vectors which are very important, and then we can derive the A and B and get C, different C values that are actually the unknown, you remember, for the vector case. And those C values are actually the solution, actually the approximation of the function. And as simple as that, now we know how finite element works. And depending on what we choose for this, we can have different techniques. You will see in a couple of minutes that, for example, this is what Fourier series, Fourier transform is all about. You choose sinusoidal functions as a basic function, and then you have for example, Fourier transform and or Fourier series, Fourier approximation of functions. And you choose another function and you have, another type of approximation. And if you choose some kind of unit vectors, you will see they are called Lagrange polynomial as the unit vectors for for unit functions, for the basis functions, let's say, you will have finite element. So this is actually the basic that you needed to know, that where this formulation comes. And later on, now we go on and you will see that it is, for example, projection Galerkin method. We know that this is how Galerkin method is written. So the thing in the finite element. And then here is a very nice example that it says we want to approximate this function. I don't want to go to the details of this example. You can read it later, but it is quite cool because we want to say linear and we have only 2 unit vectors. So a linear equation is something like this, ax plus b. So you have only 2 basic functions, which is this one, psi 0, and psi 1, x and 1. So we have actually n equals 1 here from 0 to 1. So this is a kind of, again, the unit vectors, the kind of approximation that we want to make. And then it goes on, it performs the Galerkin method. So kind of integrations on all the unit vectors, and then we assemble the A matrix and the B matrix, the B vector, let's say, using the same principle. And by doing that and then solving the whole system, we can have a linear approximation of a function. So I'm sure that you never had, you never had such an insight into, for example, these kind of perspective into linear approximation of a function. It can be seen from this perspective as well, which is quite nice. And this is actually the foundation of finite element. So here it goes for the implementation. I don't want to go and discuss the implementation. This is quite nice, very efficiently implemented using SciPy. We have already talked about SciPy in videos. And then here it says, one of the main conditions, it says orthogonal functions. One of the main things I said that in the beginning of the video, at the beginning of this notebook, that one of the main characteristics of the functions, of the unit functions, is that they should be perpendicular. So it's orthogonal. It's mentioned here. You see, if I is not equal j, the inner product of psi I and j should be 0. So for example, when we have unit vectors I and j, and even k, for example, in 3D space, like this, what is very important to notice here is that they are orthogonal. And that's why these are the unit vectors of this 3D space. And for Fourier transform or Fourier series, when we use sinusoidal functions, like in this case sine of pi x, 2 pi x, and 2, like it continues to n plus 1 pi x, they are perpendicular. And as a result, this can be a nice function space for basis function. So we can use this basis function instead of psi I, and then we use this to approximate different functions. So this is exact, and this is the Fourier approximation of that. You can see more examples here. So quite simple. You can find implementation here. Also, you can also derive it using manually. But what is really important here is actually the missing point is that you see that it doesn't end. So it starts from 0 instead of, for example, 9 here. And that's where the concept of boundary condition can enter this discussion. And this is what it tries to emphasize here, the Bx. And you can easily, by knowing the value at the 2 points, the ends of this, the 2 ends of this line, you can have a linear interpolation or, in any order, and try to add it to the approximation that we wanted to have. So we can see that this part is actually so this is the approximated function. This is the previous approximation that we knew how to do that. And then this is a new part for boundary condition that it can enter the equations as simple as this. So instead you have this one equals, so in this case it is A equals B, this is A equals B, and B this time contains also the boundary conditions, and this is X. So this is a new perspective into looking at AX equals B in finite element numerical computing. And that's why I said that this is a great book and one of the best, or the best I've read so far. So by doing that, you can see that the approximation is exactly is very similar to the exact solution. So this is actually the numerical computation of that with the reference to the files, and it says an interpolation comes into play because sometimes you want to have, like as we discussed before, you want to have like the function. In this case, you can see that it's a function of is, and is is actually just a limited set of points, and that's where the finite term comes into play. We have finite difference, finite element, and if you want to use that, we need the concept of interpolation. The technique is exactly the same, but this is what happens when you want to implement it in a computer program, and so this is a very trivial. But it's good to know that it's actually called interpolation when you want to implement it. So we want to finalize this discussion, and that's where I want to show you the kind of basis function that is used in finite element. So finite element is actually the function approximation that I showed you with Lagrange polynomials as the basis function. As simple as that. So the Lagrange polynomials are a kind of polynomial that are invented by Lagrange. You can see here. Oh, sorry, by Euler. It says it's rediscovered by Euler. Sorry. So which has a very nice property, and the property is if you have like psi x, psi I, x s, the function, the polynomial is 1 when I equals s and is 0 when I is not equal s. And this is a very important property. If you know finite element from before watching this video, now you may know that this is actually the property of shape functions, and shape functions in finite elements are actually Lagrange polynomials. So this is a definition of Lagrange polynomial. If you think about it, you can see that why it has this property. I don't want to discuss that, although it is very simple. So with this property, we can see that they are orthogonal because they are actually 1 in only one direction and 0 in other directions. So similar to ijk, they're only 1 in one of the directions. So it's very similar to this concept. And then using those principles, you can start to have like the function approximation like what we did before. So with the polynomial, now you can see that this is actually some examples that are done using this Lagrange polynomial, and that's it. And here you can see that the problem is actually the boundary condition and also the degrees of the degree that we choose, because you can see that it has different degrees or different number of nodes that you can use depending on n. Then you can have different precision for the type of approximation that you perform. And there is another type that is not used in finite element, but it's nice to see. It's called Bernstein polynomials. This is actually defined like this. And then you can see that this is also the same concept that you can see here. So if these are the function, you can see that they are only, for example, for this purple one, for this one, you can see that if these are the nodes, it is 0 elsewhere, and it has a value, it's close to 1 only at this node. So for example, for black, it has values here, but is 0 on the other nodes. So that's actually the property that we are looking for. So if it's difficult to imagine, it's difficult to understand. For example, for ijk, you have 1, 0, 0. You see that it is 1 only in one of the directions. And for j, it is 0, 1, and 0. So that's why these are actually the basis functions, so basis vectors, unit vectors, because they are one in only one of the dimensions. So function approximation in this regard can be seen as, approximating a vector in n dimensions. So that's it. And then in the second notebook, it says for higher dimension, it is exactly the same. In 2D and 3D, we can have instead of single integral, we have double integrals, but the principle is exactly the same. And in the second notebook, function approximation by finite element, the thing is, it discusses the same concept as the previous notebook, previous chapter, but in this case it discusses that we need to define this Lagrange polynomial. So this is a similar concept. You can see that these are the Lagrange polynomial that you can see that there are only one at one of the points only. So if you imagine that these are the nodes or the division in space or the number of dimensions, if you want to have the analogy to vector geometry, then it is actually one in only one of the elements. And this one is, for example, 0 and 0 elsewhere. So it is this one. You can see that it is 1 here and this one is 1 here. So probably it's worked better if I had not this one. So we have nodes only on these regions. So you can see that it is 1 here and 0 elsewhere. And we have a node also here. And that's why you can see that it is actually, we have 1 here, and 1 here. Approximated using, so it is actually the sigma of C and then psi I. So you can see it is actually from 0 to 3, or more precisely, it should be 4, because we have also two nodes at in the beginning and in the end. So that's actually how it works in finite element. And in finite element, we divide it into nodes, and then nodes are assembled into elements. These are more, implementation perspective. In this chapter, you can see that it implements a finite element program. It is a very nice implementation. So if you want to understand it in details, I highly recommend that you follow this implementation. I don't want to go for that, but you can see that also inside an element, which is actually here, we have 3 nodes, this one, and this one. And you can see the values. For example, the green psi 4 is actually 1 here only. And for example, phi 3 is 1 here and 0 elsewhere. And phi 2 is 1 here and 0 elsewhere. And then this is something that we discuss in the next video. This is the derivative of this piecewise function, and then the derivative plays an important role in when we want to talk about weak formulation. This is the reason that we need that weak formulation actually. So these are the properties of phi. We already discussed it, and then this is how it should be implemented in a finite element program. So it is actually dividing the space into nodes and then defining the basis function on that. So in this case, Lagrange polynomial, and then trying to get the value of each C. As I said, each C, like this one, C by phi I, by deriving ax equals b, and this x is actually the c. So this is actually what we are seeking for in finite element approximation of functions. So I think there are some examples here. These are, again, this is called shape functions in finite element, but now you know that they are all linear basis functions. So this is the property, the way that you can easily write the equations for these things. And this equation can enter all the process that we had for example, integration of 2 basis functions, and then equals to the integration of f multiplied inner product of f to the basis function. So yeah, let me scroll down. You can see that these are the calculation. This is how you can write the phi for boundary nodes. So the boundary condition can also come into play. And then in the end, if this is f, this is what we have as the approximation of f using p1 values. So p1 and p2 is actually, this is also nice to know. So this one is for p1. So linear shape functions, linear basis functions. And for P2, we want to go for P2 values. It means that we have 3 nodes inside the element, allowing us to define a quadratic function instead of a linear one. So we can have a more precise approximation of functions because we have, basis functions in higher orders, in higher dimensions, let's say. And yeah, so here it says that you can see the 2 elements, only 1 element here and 1 here, and 4 here using P1. And then later on it also discusses it. So this is for assembling of the A and B vectors and matrix. So these are all the implementation thing. Let me scroll down faster. This is the implementation. I don't want to discuss it, and you can see that in the end, the A matrix, because now you know why, the A matrix, when you assemble it, so this is A, is actually sparse because it has elements only on the regions that are close to the diagonal, and that's because of the property. So remember that A was equals to psi I inner product by psi j. And that was actually an integration of that. And then it means that, because of the properties and depending on the number of elements we have in each node, in each element, a number of nodes we have in each element, this is only 3. The width of that is only 3 because when you start to have it for all the nodes, the rest will be 0 because actually this is related to this. To the figure that we saw in the beginning, because there are 0 outside of the element. So they have value when these functions imagine that they are getting multiplied by each other. They have values when they are inside the element. Outside it is 0, and that's one of the properties of the Lagrange polynomials. So yeah, that's it. And then here we have different approximation. In this case, there are P1 values that we use only linear elements, linear basis functions. Now we can use more accurate terms. So linear basis functions, it is this approximation with correct values for boundary condition, and this is for actually quadratic basis functions, meaning the P2 elements. And we can have also higher order elements, and I will show you later. And this is actually talking about the sparsity of the matrices, and that's why we need special techniques. For example, it says here that SciPy has some sparse matrix storage, because if you want to store the whole matrix, it's a lot of waste in storage, in space, for I/O, for disk. And there are some special techniques, we have already discussed it in the SciPy video, for storing sparse matrices. And now you know the reason that this diagonal only has values and not the rest of the elements. And then it goes for implementing a general concept for that. So more examples of the implementation. And when it goes to 2D and 3D, the concept is the same. You have nodes here defined on this intersections, and depending if you want to have higher dimensions, you can have. So these are really with P1, and then with P2 we will have more nodes. And then, this is how it works in 2D, and then 3D, the same thing. So we actually have different nodes on which we can have different basis functions, and those basis functions can contribute to approximate the main function that we want to have actually an approximation from. So we can see that this is actually the 2D implementation, 2D construction, and so approximative function based on a mesh. So now with these things, I think it's more or less clear that what a mesh is, what a basis function is, and then later on in the next video I will talk about is how we can take advantage of these concepts to solve partial differential equations. And here is a demonstration of various diff elements. So 2D P1 is this one, only values we have on a node, and for P2, as I said, we have all the center of edges. Similarly, we can have like P3, P4, P5, and P6. So just increasing the accuracy of the approximation, because we can have like higher order basis functions. And in 3D, it is similar. So it is P1 and in this case P2. So I hope that you find this useful, although it was long, because actually it was important to know the basis, the concept of basis function and why it is important in finite element. And then that's it. That's all. That's the concept of finite element. And in the next video, I will show you how we can use these concepts to reduce the order of partial differential equations, and then we can easily extract ax equals b from differential equations or partial differential equations as well. So in these two chapters we discuss approximation of functions, and in the next video we will discuss approximation of differential equations, and you will see that they are very similar. I hope you find this useful. Make sure to check out these two notebooks, and then I'm sure that you will enjoy it. Have fun. See you in next videos. Bye.